Hello, I'm glad to see you again at our avionics engineering course. And today we have lecture number number 9, right? So uh, the topics of today's lecture is accelerometers. The acceleration of a vehicle can be determined by measuring the force required to constrain a suspending mass so that it has the same acceleration as the vehicle on which it is suspending, or using Newton's law, force equal mass times acceleration, right? Okay, nice. So the measurement is complicated by the fundamental fact that it is impossible to distinguish between the force acting on the suspending mass due to the Earth's gravitational attraction and the force required to overcome the inertia and accelerate the mass, right? So that it has the same acceleration as the vehicle. The vehicle acceleration A being produced by the vector sum of the external forces acting on the vehicle, namely the propulsive thrust T, lift L, drag D, and the gravitational force mg acting on the aircraft mass m. Here you see the bold print denote the quantities that means a vector quantity. Okay, so we may write T plus L plus D plus mg proportionals ma, from where we can find our expression very simple for acceleration. Okay, thus the vector sum of the external force excluding the gravitational force divided by the aircraft mass, that is T plus L plus D over M, is known as the specific force. The force Fa required to constrain the suspending mass Ma is thus given from this expression, Fa plus Mag proportions Ma times A. In this case, we make both sides divided by from Ma, and we get Fa over Ma plus G is the same as acceleration, and get us expression T plus L plus D over M is plus G. And hence, we may found expression very simple for Fa. So, the accelerometer will thus measure the specific force component along its input axis and not the vehicle acceleration component. Do you agree with me? Very. So, in this, it is thus essential to know the magnitude and orientation of the gravitational vector with respect to the accelerometer input axis in order to compute the vehicle acceleration component from the accelerometer output. And only if the accelerometer input axis is exactly orthogonal, it means each direction has the 90 degrees to the gravity vector. In our case, we have a horizontal direction, so that there is zero gravitational force component. Will the accelerometer measure the vehicle acceleration component along its input axis? A simple spring restrained pendulous accelerometer is shown schematically in this slide. This comprises an unbalanced pendulous mass, which is restrained by the spring hinge so that it can only move in one direction. that is, along the input axis. The spring hinge exerts a restoring torque, which is proportional to the angular deflection from the null position. When the case is accelerating, the pendulum deflects from the null position until the spring torque is equal to the moment required to accelerate the center of mass of pendulum at the same acceleration as the vehicle. This simple type of accelerometer is typically oil-filled to provide viscous damping, so that the transient response is adequately damped. An electrical position peak-off measures the deflection of the pendulum from the null position and provides the output signal. The transfer function of the simple accelerometer described in a simple quadratic Lec filter of the type output over the input inclination proportional of this expression K naught. This is the accelerometer scale factor, and the undamped natural frequency omega naught proportional K over I. Here K is a torsional spring stiffness of hinge, and I is the moment of inertia of pendulum about hinge axis. The simple spring restraint accelerometer is used in applications where the accuracy requirements are not demanding, nearly 1 to 2 brackets. The maximum angular deflection of the pendulum from the null position is limited to about plus minus 2 degrees to minimize cross-coupling error. This results in a maximum cross-axis coupling error of sine 2 degrees. That is approximately 3.3% of any acceleration acting along an axis normal to the input axis. So no matter in which direction, vertically, horizontally, or another side, right? So the acceleration input rate thus determines the spring stiffness or rate, and hence the bandwidth of the sensor. For example, consider an accelerometer with a maximum input range, say plus minus 10 G, an undamped natural frequency of 25 Hz. So the same basic accelerometer design for an input range of plus minus 3G would have a bandwidth of only 14 Hz approximately, and being reduced by a factor of square root 3 over 10. The above shortcomings in terms of accuracy and bandwidth can be overcome by the closed-loop torque balance operation of the accelerometer. The deflection of the pendulum from its null position under an input acceleration is sensed by the position peak-off and the peak-off signal after amplification and suitable dynamic compensation is used to control a precision torque motor to maintain the pendulum at or very near to its null position. Measurement of the torque exerted by the torque motor to balance the inertia torque resulting from accelerating the pendulum's mass so that it has the same acceleration as the vehicle, then enables the acceleration to be determined. Strictly speaking, the specific force is measured. Pulse torque operating of the capture amplifier is generally used giving a pulse rate output which is directly proportional to the input acceleration. Each pulse represents a velocity increment. For example, 0.05 meter per second, or approximately 0.1 kilonewtons, providing an incurrent integration. The construction of a typical modern torque balance pendulous accelerometer, also referred to as a servo accelerometer, as shown in this slide. The accelerometer consists basically of a beam fabricated from fused quartz, which is suspended within the case by a very low stiffness flexural hinge, as shown in this illustration. Quartz exhibits zero hysteresis and consequent increased bias stability compared with a metal spring hinge. A capacitive position peak-off is used to measure the displacement of the pendulum's mass, also referred to as the proof mass or seismic mass from its null position. All the generation inertial accelerometers generally use inductive peak-off for this function. Torques are applied by means of moving coil of permanent magnet torque, similar to a loudspeaker driver, with the coil fixed to the beam. Thin flexible conducting ligaments enables electrical connections to be made to the torque coils and the capacitive peak-off plates. A mechanical damper is generally incorporated to supplement the dynamic compensation in the capture amplifier in providing a well-damped response, typically around half critically damped. Bandwidth is typically around 500 Hz. A temperature sensor is generally incorporated in high accuracy accelerometers to enable temperature-dependent scale factor errors to be corrected. Typical size is around 2.55 centimeters or 1 inch diameter and 2.54 centimeters or 1 inch in length. Okay, nice. Accelerometers used in very severe environments with very high vibration and shock levels are generally oil filled to increase their robustness. Solid-state accelerometers fabricated from silicon using semiconductor manufacturing technology are now being widely used for lower accuracy applications. The technology offers very small size and low manufacturing cost. This slide illustrates the construction of a solid-state silicon accelerometer. The capacitive peak-off senses the deflection of the pendulum under acceleration, and electrostatic forces are exerted to maintain the pendulum near the null position by applying DC voltages to the case-mounted electrodes by means of the caging. The torque balance loop of an electromagnetic torque balance type of pendulous accelerometer is illustrated in block diagram from this figure. For persons who wish to derive the accelerometer transfer function, it's this application only. But for this moment, this out of our lecture. No? Okay, so that if somebody interested in more detail, they may ask me during the individual case, right? So the accelerometer loop gain must be sufficiently high to keep the pendulum excursions from the null position very small under the vibration environment. Significant rectification errors can otherwise be introduced as the accelerometer will sense a component of the vibration at right angles to its input axis, which is proportional to the pendulum displacement from null. A simplified explanation of this is set out below. Assume, for simplicity and for worst case, that the vibration is at 45 degrees to the accelerometer input axis, so that the along and cross-axis vibration component are equal and are given by this explanation. Acceleration A proportionals A maximum times sine omega t. Here, A maximum is the peak value of the vibration acceleration. A acceleration and omega is the angular frequency here. The displacement of the pendulum from null is given by the next expression. Epsilon proportional A maximum over K times sine from omega t plus P, where the K here is the dependent on the loop gain at frequency omega. And F is the phase shift between epsilon and A. Then cross-axis acceleration, in this case, will be described as next expression. Epsilon times A sub max times sine omega t, and will be proportional in the side. A squared maximum over K times sine omega t times sine omega t plus psi. The product, this product, sine omega t dot sine omega t plus psi, has an average value of 4 sine cosine psi over 2, so that a proportion to the input vibration is rectified. And this error source contributes to the G squared error sensitivity of the accelerometer, as it is proportional to the square of the vibration acceleration, right? So that we have square vibration acceleration. One of the attractive features of a step-down system is that economical failure absorption configurations are available. One such configuration is an arrangement of 6 single-axis ray gyros and 6 accelerometers with their input axis skewed with respect to the principal axis of the velocity, axis of the vehicle, so that they form equal solid angles, as we can see from this figure. The configuration is sometimes referred to as a dodecahedron. Motion about any principal axis is sensed by 4 sensors, so that it is possible to detect and isolate up to 2 failures without loss of capability. The sensor supplies and electronics are entirely independent, so that common failures are precluded. Each gyro in the dodecahedron configuration senses 2 body rates, and each body rate is sensed by 4 of the 6 gyros. The gyro output denoted by the letters A, B, C, D, F are functions of the body rate, as we can see here in this slide. Here alpha is equal 31.72 degrees. Exactly we can see as this value after dot 716747. At this the angle between the gyro inputs axis and the body axis. By the way, there are thus 6 equations in 3 unknowns, which can give 2 independent measures of each body rate. Sophisticated algorithms can be used to isolate a failed gyro and recombine the data from the remaining sensors in an optimum way. There are other configurations of skewed sensors which are also used. For example, three orthogonal sensors with their input axis aligned with the aircraft principal axis, and four sensors with its input axis skewed at 45 degrees to the principal axis. Two such independent sensor sub-assemblies and can tolerate three gyro failures. And now we became to the next topic today's lecture, attitude derivation. The measurement of the aircraft's attitude with respect to the horizontal plane in terms of the pitch and bank angles and its heading, and that is the direction in which it is pointing in the horizontal plane with respect to north, is essential. The spatial attitude of an aircraft is specified by the three Euler angles, which are defined in our dynamics dynamical form, right? So that in this figure, we can see the aircraft that is the first rotated in the horizontal plane through the heading or azimuth angle side. Then rotates about the pitch axis through the pitch angle theta, and then rotated about the roll axis through the bank angle P capital. The rotation must be made in that order as they are non-communicative, and that is a different orientation would be obtained if the rotations were made in a different order. So there are two basic inertial mechanizations which are used to derive the Euler angles to the required accuracy. The first method, which is known as a stable platform system, has the gyros and accelerometers mounted on a platform which is suspended in a set of gimbals. The gyros then control the gimbal servos so that the platform maintains a stable orientation in space, irrespective to the aircraft maneuver. Angular position, because on the gimbal, and then provide a direct readout of the Euler angle. A typical stable platform is illustrated here in this slide. The second method is known as a strap-down system, as it has the gyros and accelerometers mounted on a rigid frame or a block which is directly fixed, that is strapped down the airframe. The gyro and accelerometer thus measure the angular and linear motion of the aircraft with respect to the aircraft's body axis. And the Euler angles are then computed from the body rate information by the system computer. But it should be noted that a stable platform system and a strap-down system are mathematically equivalent systems. And that's very nice. The function of the mathematical gimbal is carried out by the strap-down system computer, which in effect contains a mathematical model of the gimbal. The stable platform mechanization of an IN, this inertial navigation system, is also easy to visualize, and so is used to explain the basic IN principle, such as Schuller tuning, about which we will be discussing a bit later. And now let's become to the strap-down system. This figure illustrates the strap-down HAHRS or INS concept. The derivation of the Euler angles from the body rates of rotation will be explained a bit later. Don't worry. So, the Euler angles, such as F, theta, psi, are already defined. And the equation relating to the body angular rate PQR to the Euler angle rate are derived and calculated. The Euler angles psi, phi, theta, and psi are defined, and so the body angular rates PQR to the Euler angle rate reflected in this equation. Equations for F dot, theta dot, and psi dot can be derived from this equation you can see on the top left corner by suitable algebraic manipulation and set out below. And we can see here. And next equation can be expressed more compactly in matrix form. The Euler angles can be then derived from the Euler angle rates by a process of integration using as initial conditions a known attitude at a given point in time. This process becomes meaningless, but however, at theta equals 90 degrees, conditions when tangent theta and secant theta become infinite. This is the mathematical equivalent of a gimbal law. The use of the three-parameter Euler algorithm is therefore generally limited to pitch angles between plus minus 30 degrees, as the error equations are unbounded, and to avoid mathematical singularity. A fully maneuvered system is therefore required where there are no restriction of the pitch angle. The limitation of the three-parameter Euler system are overcome by the use of what is known as the Euler four symmetrical parameters to define the legal attitude. It can be shown that an axis set may be moved to any required orientation by a single rotation about a suitable position angle, axis. Let this axis make angles cosine 1 over cosine alpha, 1 over cosine beta, and 1 over cosine gamma with the inertial axis OX naught, OY naught, and OZ naught respectively. Let a single rotation mu about these axes bring a moving axis set from OX naught, OY naught, and OZ naught into coincidence with OX, OY, and OZ. So we have the set whose orientation it is desired to specify. The Euler four symmetrical parameters are given by this expression. Then E0, E1, E2, and E3 can be used to specify the attitude of the vehicle with respect to OX naught, OY naught, and OZ naught. And the following relationship with the Euler angles can be derived as these three expressions: for sine theta, for tangent psi, and tangent phi. It's maybe a bit boring expression, but you should be only understand it. No need to memorize. Okay. So, and this can be shown as matrix expression here. Because four parameters are being used to describe the orientation when only three are necessary, a constraint equation exists in this form. E0 squared plus E1 squared plus E2 squared and plus E squared should be equal 1. Right? These two equivalent equations have great advantages over the equivalent Euler-Angle equation. First, they apply to all attitudes. Second, the error equations are bounded by the constraint equation. And third, the numerical value of each parameter always lies in the range from -1 to +1. So easing the scaling problems in the computing mechanization. And we have that equation can be rearranged into the matrix form, as you can see here on the top left corner. These can be written more compactly as x dot proportional A times x. Here we have x as a vector E, A as a scarf from this expression, yes, and the both capitals here of x and I, it means matrix. This equation can be solved by approximate integration techniques by assuming P, Q, R are constant over a short period of time, say delta t. So we have short period of time delta t from time t n plus time tn plus 1. The predicted value of x at time tn plus n plus 1 is given by these first expression. Here under my picture, you may found as the xn plus vector A times vector xn times delta t. Another say we may rewrite x sub xn as this small expression. 1 is a unity matrix here. And 1 plus A delta t is in fact an approximation to the transition matrix, which relates the value of the state vector at time t n plus 1 to the value at time here. So the incremental angular rotations measured about the row, pitch, and yaw axis are denoted by delta P, delta Q, and delta R respectively. The pulse torque DTG and RLG and the IFOG all function in the integrating rate gyro. So that we have integrated rate gyro. But generally it's very simple. PDT, QDT, and RDT. Hence, the approximate transition matrix will be rewritten in this form. And hence, we can write next form. First vector for E, for Tn plus 1, what next integration, get us this expression matrix times in previous vector V in previous condition. The performance of the numerical integration algorithm can be further improved by using second-order Runge-Kutta algorithm or four-order Runge-Kutta algorithm, where very high accuracy is required, and by decreasing the integration time increment. It's time increment delta t with a more powerful computer. Today, generates without problem. The constraint equation, it's E0 squared plus E1 squared plus E2 squared plus E3 squared should be equal 1. This is used to correct the transition matrix for the accumulated computational error in the integration process to maintain the orthogonality of the computed axis. The asymmetrical Euler parameters are also mathematical quaternions, as it can be shown that they are made up of the sum of a scalar quantity and a vector with orthogonal components. The value of the Euler angles psi, theta, and f are then calculations from the next three equations here. The corresponding initial values of Euler parameters, when the initial value of Euler's angles, namely psi, theta, and phi, given by this system of four equations. For example of an attitude algorithm. A simple work example is set out below to show how the attitude is derived from the Euler four-parameter transition matrix to give a practical appreciation of the mass involved in evaluating the matrix for those who less familiar with matrices, right? So generally very simple. Assume at time Tm, the values of the four Euler's parameters represented with these vectors. We may check E naught squared plus E1 squared plus E2 squared plus E squared. We can this one exactly O.81, O.09, O.04, right? And plus O.09. Sorry, here it should be O.01. Add sum that get us square sum, get us 1. You may check this, very simple. And the values of the body angular rate are, and this you may see, P 1 radian per second, Q 0.04 radian per second, and R 0.05 radian per second. Iteration period very, very small, 0.01 second, and delta P 0.01 radian, delta Q 0.304 radian, and delta R 0.305 radian. The Euler angles at time Tn are calculated using our equation and as substituting the approximate value for E naught, E1, E2, E3, from which we can get this system. Psi equals 36.869, theta 0 exactly, P 36.8698 in fact. So the transition matrix we may be represented in these big matrices. But generally very simple to calculate. So why it's using a very popular. And hence at time t n plus 1 at the next step, E naught will be represented as this expression. In other case, I forgot this open case. E naught will be equals O.89. Evaluating the updating matrix yields this expression. And we will check as the E naught square plus E1 square plus E2 plus E square, it generally gets us 1 after the 4, 0 get us 25. Those values, it's very, very exactly. So the small error in this constraint equation is due to using the first order approximate solution. And the Euler angles at time Tn plus 1 we can get in this expression. Psi get us 3691, theta 0.30963, and P 37 plus 4428, 33 angles. The process is repeated at each iteration period. And now let's start with another subtopic for today's lecture, generation of strap-down equivalent stable platform. You know, the next figure illustrates the computational process involved in generating an equivalent stable platform within the step-down system computer. The integration of Euler parameter rates to yield the Euler parameters, as explained, enables the direction cosine matrix DCM to be computed for the aircraft axis to local north, east, down, NED axis, conversion, and vice versa. This enables the step-down accelerometer measurements like AX, AY, AZ of the aircraft acceleration components along the aircraft body axis to be converted into the aircraft acceleration components along the local NED north-east down axis. In our case, we can A sub N, A sub E, and A sub D. The computing system thus provides the equivalent of accelerometers mounted on a stable platform, with the input axis aligned with the local NED axis, north is down. So, the direction cosine matrix for converting the local NED axis from aircraft body axis may be represented by this matrix. Look at this one. And thus, the aircraft acceleration components with respect to the local NED axis are given by more simple expression like here. Gyros measure angular motion with respect to an inertial axis frame. That is an axis frame which is fixed in space. It is therefore necessary to rotate the gyro-derived reference frame at the appropriate rates, and so that it stays aligned with the local NED axis because of the Earth's rotation and the vehicle's motion over the spherical surface on the Earth. Right? Nice. The latter corrections are known as the vehicle rate corrections. Earth rate and vehicle rate corrections will be converted a bit later. Maybe like next lecture. In the case of a stable platform, these corrections are made by processing the vertical and azimuth gyros at the appropriate rate, as explained already earlier. In the case of a step-down system, the Earth rate and vehicle rate corrections are converted to the approximate DCM to the coordinate frames rate with respect to the aircraft axis. These coordinate frame rates are then summed with the aircraft body rates like PQR, so that the subsequent integration will yield the aircraft altitude with respect to the local NED axis, known as the initial condition. The DCM for converting the coordinate frame rate for the Earth rate and vehicle rate from local NED axis to aircraft body axis is given by this last expression of the bottom. It is shown that the Earth rate corrections about the north-east down axis are given as a omega cosine lambda, omega sine lambda, respectively with omega is the Earth's rate of rotation, and lambda here is a latitude. The vehicle rate corrections are VE over R minus Vn over R and minus VE over R tangent lambda about the north-east down axis, where Vn and VE are the components of the aircraft's velocity along the north and east axis. and r here is the radius of the Earth. And hence, the vehicle rate and Earth rate corrections about the aircraft XYZ axis are given by this expression. The initial value of the direction cosine matrix between the aircraft and the local NED axis is given by this expression. Whereas the S here is a sine and C is a cosine. So we're using this simply for more shorter and more compact form. Okay? S sine, X C cosine. So the strip down system accuracy is the initial value of the direction cosine matrix between the local NED axis and the aircraft axis is given by this expression. And next, let's start another subtopic called the digital processing of attitude algorithm. In our case, the step-down system accuracy is critically dependent on the accuracy of the digital processing involved in the numerical solution of the attitude algorithms. Computer performance was in fact a major limitation in the implementation of step-down systems until the advent of high-speed microprocessors. The major error sources in the digital processing will be briefly discussed in today's lecture, and together with the methods used to minimize these errors. And first of all, it's commutation. Errors arise in digital processing because of the non-commutativity of angular motion. A different attitude is attained if a series of rotations about the body axis are made in different order. Commutation errors are introduced in the numerical processing because for each solution update of the transformation matrix, the processor operates sequentially on the input angular rotation increments in a fixed order. And this may not correspond to the actual time ordered sequence in which the angles were accumulated in past, particularly when subjected to cyclical or repetitive inputs such as conical motion, which can result in a rectification drift of the transformation matrix. These communication errors can be minimized by decreasing the angle increment size involved in each computation. Coning motion is briefly covered in the next lecture. Integration. Errors arise in the integration because of using discrete approximate solution of the continuous process and equations which have no analytic solution. These errors are minimized by using sophisticated integration algorithms like Runge-Kutta force order, and by increasing the update rate. Another thought is the roundoff. These errors are due to the finite resolution of data and rounding off the computations to the value of the least significant bit. This causes a random walk error built up in multiple computations. Double precision working, as minimum 32 bit for critical operation, is used to minimize this error. And quantization. These errors result from the process of converting the analog output of the sensors into discrete increments, which can be input as a series of pulses into the digital computer. And this quantization process causes the input to the computer to always swag the outputs of the sensors. The average value of this quantization, or sometimes we may say as a sensor storage error, is 1/2 of the quantization angle. You know, this information is not lost, but received in the next update cycle and result in a quantization noise in the output that needs to be modeled for the best performance. And you know, these errors are minimized by decreasing the quantization angle and mathematical model. So let's start another subtopic called Coning motion. A brief explanation of Coning motion is set out below in a view of its importance as possible source of error. Coning motion results from the vehicle being subjected to angular oscillation of the same frequency about two orthogonal axes with 90 degrees phase difference between the two motions. The motion of the third orthogonal axis of the vehicle describes the surface of a cone and hence the term conical motion. So why we have cone? Suppose the motion measured by the gyrus is as follows. And so suppose the motion measured as follows, as we can see here. P equal naught Q A omega cosine omega t are proportional A omega sine omega t. And referring to the next equation as here, theta dot proportional Q cosine t minus R sine t, assuming the steady state Euler angles are all zero and theta and f are small angles. And so we can rewrite as theta dot is the same as the Q angle, proportional A omega cosine omega t. Integrate yields us theta. Theta get us A times sine omega t. And referring to equation P dot equals P plus cosine P times tangent C plus R cosine P tangent C, theta. And for small angles, we can write as P sine P, it get us P, tangent theta, simply theta, and cosine P get us 1, approximately, and neglecting second order terms, as we can see here, F dot equals R theta, or A omega sine omega t times A sine omega t. Another say we can rewrite omega dot proportional A squared omega 1 over 2 times in parentheses 1 minus cosine 2 omega t. And hence, average value of rectified operation rate get us this simple expression. P dot get us A squared omega over 2. The errors induced by Coning motion in step-down systems arise essentially from errors in computing the motion profile due to the non-commutativity of angular rotation. For example, a cyclic Coning motion resulting from angular motions of 1 degree amplitude and 1 Hz frequency measured by gyrus with a scale factor error of 0.01% results in a rectified drift rate equal from this expression 0.01 over 100 times 1 over 2 times 1 over 57 and 3 squared times 2 pi 1 and get us. So we get degree per hour, and that we can get 0.02 degrees per hour, which is significant in an INS, inertial navigation system. Next subtopic today's lecture, attitude with respect to local north, east, and down axis. The aircraft pitch and bank angles are required with respect to the local level plane. That is a plane which is normal to the local vertical, defined as a line through the aircraft to the Earth center. The aircraft heading angle is generally required with respect to the true north, that is direction of the local meridian pointing towards the North Pole. The local meridian being a circle around the Earth, which passes through the North and South poles and aircraft's present position. It is therefore necessary to convert the gyro-derived data, which is with respect to inertial axis, to an Earth reference axis frame. There are 3 basic directional references which are used to align an HRS or INS, and this comprises the Earth's gravitational acceleration vector. This is sensed by the accelerometers and enables the local vertical to be determined. Earth's angular velocity vector. This can be measured by the gyro, provided by they are the sufficient accuracy, and enables the aircraft heading to be determined by a process known as gyrocompassing. It will be shown as that heading accuracy of 0.1 degrees. However, requires the gyro bias uncertainty to be less than 0.01 degree per hour. The technique is therefore not suitable for AHRS using lower accuracy gyro. And finally, Earth's magnetic field. This enables a hidden reference to generally within 0.7 degrees accuracy to be established at latitudes below 60 degrees north or south of the equator. This figure illustrates the basic Earth reference axis frame, generally referred to as a local level north slave axis frame, or sometimes called, not sometimes, very popular last time, as a north-east down axis, NED, angular rate correction for the Earth's rotation. So this figure and accompanying vector diagram shows the Earth's angular velocity vector omega, yes, as you can see, omega, can be resolved into 2 components. First, components about the north pointing axis, as we can see here on the north, omega times cosine lambda, where lambda is the latitude angle of the aircraft position. This correction must be applied to the computer-derived axis of the vertical stable platform to maintain a level state. As an example, at a latitude of 51 degrees and 30 minutes north from London area, the Earth rate component about the north axis is 15 times cosine 51 degrees 30 minutes degrees per hour, and get us 9.3377 degrees per hour. Or in this case, we may simply say omega equal, our omega equal 15 degrees per hour. And another component about the local vertical axis is omega sine lambda. This correction must be applied to the virtual stable platform if it is desired to maintain in pointing north. But it should be noted that there is zero component of the Earth's angular velocity about the Earth's pointing axis. And this forms the basis of the gyrocompassing alignment technique, which is explained a bit later. And now let's describe vehicle rate correction. This figure on the left side illustrates how the local vertical rotates in space as the aircraft flies over the surface of Earth, because the Earth is spherical. The angular rates of rotation of the local vertical with respect to the inertial axis are equal to Vn over r about Vn over r about the east pointing axis. Here Vn is a northerly component of the aircraft velocity, and r is the radius of Earth. Another component we have here is about north pointing axis, V is over r, where VE is the easterly component of the aircraft velocity. These angular rates are referred to as the vehicle rate. It is therefore necessary to rotate the virtual platform about the east pointing and north pointing axis at angular rate over Vn over r and VE over r, respectively, in order to maintain the virtual platform locally level as the aircraft moves over the spherical surface of the Earth. The magnitude of this vehicle rate correction term is more easily appreciated by expressing the aircraft's velocity in kiloknots, nautical miles per hour. Bearing in mind 1 nautical mile is equal to 1 minute of r of the Earth's surface. So why? That's classically in ship and aviation now using not metric system at this imperial. For example, an aircraft with a ground speed of 600 kiloknots and a track angle of 30 degrees has a northerly velocity component Vn 600 cosine 30. That is, get us 519.6 kiloknots. And in easterly velocity component, VE get us 600 times sine 30. That is, get us only 30 kiloknots, approximately 2 times less. A correction rate equals 519 over 60, that it get us 8.66 degrees per hour about the east axis, and get us 300 over 60, that is 5 degrees per hour about the north axis, is required in order to maintain the platform, real or virtual in case of strap-down system local level. An external source of velocity, such as a Doppler radar, or less accurately air data, can be used to derive the northing and easting velocity component for the vehicle rate correction term. The Doppler or air data derived velocity components would generally be combined with the inertially derived velocity component from the accelerometers, as will be explained a bit later. The use of very high accuracy gyros and accelerometers enables the velocity components to be derived directly from the accelerometers and fed back to correct the vertical reference so as to form a Schuller-tuned system, and is explained later. So there is also a vehicle rate correction, VE over R, tangents lambda, about the local vertical or down axis. which must be applied to the virtual platform in order to maintain the north reference, as we can see here in this figure. So, through the latitude angles, we can get this expression. It can be seen that the VE over R times tangent lambda term increases rapidly at high latitude and becomes infinite at the pole when lambda equals 90 degrees. Alternative coordinate systems are used to overcome this limitation at high latitude in case of more than 75 degrees. This is explained in the next part of lecture, and it should be noted that this term is generally referred to as a meridian convergence term. And now let's start another subtopic today's lecture, vertical monitoring. As mentioned in introduction, the basic vertical reference is the Earth's gravitational vector. The platform, no matter real or virtual, can thus be initially aligned locally level using the accelerometers to measure the tilt errors from the local vertical. The accelerometers act in a sense as spirit level. This assumes the process is carried out when the aircraft is stationary on the ground or in straight and level flight at constant speed and the aircraft is not accelerating. However, any aircraft accelerations would result in the accelerometers defining a deflected or dynamic vertical because the accelerometers are unable to distinguish between the gravity component and acceleration component. An ideal vertical reference system using gyros with negligible drift or bias and entities, once initially aligned with the local vertical, would continue to measure the aircraft attitude with respect to the local vertical using the gyros alone. Assuming the Earth's rate and vertical rate corrections were applied without error. In practice, the Earth's, however, gyro drift and errors is applied to the necessary correction terms would cause a progressive build-up in the vertical error unless some means for monitoring the vertical error and applying correcting feedback were incorporated. In fact, a compromise between accelerometer measurement and gyro measurement of the vertical is always used. The next part of lectures should explain how Schule tuning enables an inertial navigation system to maintain a very accurate vertical reference irrespective to the aircraft's acceleration. AHRS systems use an independent source of the aircraft velocity, such as a Doppler or less accurately air data system, to monitor the vertical reference. The aircraft velocity components are derived from the AHRS accelerometers in the same way as an inertial navigation system, and the velocity differences are then used to correct the vertical reference. The method is known as Doppler or air data over inertial velocity mixing and is covered a bit later. The very high accuracy gyros and accelerometers, which are essential for Schule tuning, enable gyro compassing to be used to align the heading reference to within 0.1 degrees of true north. The very large gyro drift rate enables an accurate heating reference to be maintained for several hours without monitoring. Gyro compassing will be covered in next lecture. The gyros used in AHRS have too high a drift rate for gyro compassing to be effective for initial alignment. Once aligned, the heating accuracy will also degrade with time because of the gyro drift rate, which can range from 5 degrees over hour to 0.1 degree over hour, depending on the AHRS accuracy grade. A magnetic heating reference is used for initial alignment and to provide a long-term monitoring of the heating by combining the gyro heating with the magnetic heating. And this will explain next lecture. And now, before the final, let's take our attention about the complementary filtering. Inertial velocity mixing explores the techniques of complementary filtering for combining the data from two independent sources of information. Other examples include combining a magnetic heating reference with a gyro heating reference. And second components, combining parametrically measured altitude or radar altimeter measured altitude with inertially derived altitude. Sophisticated mixing systems exploring Kalman filters to control the gains of the mixing loop are frequently used, particularly in view of the computing power now available to implement such systems. It is appropriate at this point to discuss the basic principles of complementary filtering. A simple order mixing system is used as an example to keep the math relatively simple. The build-up to the more powerful second order, or third order, or even fourth order and above systems with variable mixing gains can then be appreciated. In this simple example, the output from the two independent systems measuring a quantity theta on the left side are designed to the theta 1 and theta 2 respectively. As their characteristic theta 1 has a low noise content and a fast response to the changing in theta. It is also subjected to the drift with time. And theta 2 has a high noise content, but has a good long-term accuracy. A method of combining of the two sources with a simple first-order mixing system is shown in the block diagram here you see. So we can write as a theta naught proportional theta 1 plus k times integral difference between theta 2 minus theta naught over dt, from which we can get next expression for theta naught. Td over 1 plus Td times theta 1 and 1 over 1 plus Td times theta 2. Here we have the T, it's 1 over K. And that is, we can write as theta naught, we'll rewrite F1 times D times theta 1, plus F2 time from D times theta 2. And here, F1 from D get us this expression Td over 1 plus Td. And the same Fd from F2 from D, 1 over 1 plus Td, which is the transfer function of a first order high pass filter or washout filter. And if F2 from D, here we say, is a transfer function of a first order low pass filter. Next, our expression of the top here, as it shows the basic concept and the response of the various elements of the system to step input in theta. The output theta naught is thus the sum of two components. First, the quantity theta 1 is coupled through a simple high-pass filter with a transfer function f1 from d. f1 for d, if you remember, td over 1 plus td, which passes dynamic changes in theta without lag, but has zero output at a DC. A constant drift is therefore DC block and has no effect on theta naught. A change in drift will, however, cause a transient change in theta naught. And second, the quantity theta 2 is coupled through a simple low-pass filter with a transfer function f2 from d to get us 1 over 1 plus td, which filters the noise present in theta 2, but preserves the DC accuracy. The accuracy theta naught thus reproduces the input theta from the sum of two complementary filtered output of theta 1 and theta 2 without lag and with a loud noise content. A constant drift on theta 1 is DC blocked, but will produce a steady state offset of theta naught to back off this drift. To eliminate this offset requires a parallel integral term leading to a second-order system. Other errors, such as a bias error, may require a third integral term to be added to the system leading to a third-order mixing system, and so on. You know, it can be seen with these simple examples that complementary filtering output is superior in either source of its output. Now, what I may say, I hope you enjoyed this lecture. Next lecture will be navigation system. And I'm looking forward to seeing you next time to continue studying our favorite course. Bye.